started. You can't hear me. That's what that means. Okay, hi. So I was saying, hi, everybody. We're going to get started. It's 1:30. I'm Julie Bernauer. This is Ming Liu. We're both from NVIDIA. Ming Liu is a researcher. You might know him for his paper on MoCA GANs. I'm a solutions architect. I worked on deep learning for large scale. And today, so we're going to have a tutorial on theory and applications of GANs, Generative Adversarial Network. And the way we're going to do it is we're going to do it in 3 parts. We're going to have a first part, which is going to be basically an introduction. I mean, for us, it's a big challenge because there's so much scientific work done that it's very, very hard to cover in such a short period of time. So what we're going to do is we're going to have a first, which is mostly introductory, first part. Then we're going to have an interlude where we're going to show you from that theory, if you have to do something simple in practice, all the kind of hurdles you can see and what happens. Then we're going to have a short break. And then we're going to have a third part where we'll tackle more advanced concepts. So at each part, at the end of each part, we'll have a few question sessions, if you wish. And the schedule is very free-form, so we'll see how it goes. Feel free to ask any question anytime, or if you feel it's too fast or so on, feel free to raise your hand and comment. Thank you very much. Ming.
Okay, let's get started. So this is the today's schedule. We will have 3 parts, as Julie said. Part 1 will be about generative modeling and GAN training. And then we will have some demo. And we'll take a half-hour break. And part 2 will be mostly on video generation and image translation. Just before we really get in start, I want to mention that GAN is crazy. This figure shows the number of papers published, about GAN. And from 2014, Ian Goodfellow published the first paper, and in 2017 we have seen more than 80 papers, and the speed is more like exponential. So, because there are so many papers, we will certainly miss some of them. And I apologize if I forget to mention your papers in this tutorial. Most of the papers are selected to tell the main story we want to tell. So it's not included only because it's not our main story, but they can be very good. And recently, there's a website called GAN Zoo. It's basically a bunch of GAN names, like Cyclogan, like Ali, PyGAN. Many works can be found from this web page. And by the way, the tutorial slides will be made available online after the tutorial, probably before midnight today. So I'm sorry that you cannot download it now. And if you have any question during the presentation, feel free to ask. Okay, so it's gonna be our outlines. So start with introduction, and we'll talk about the GAN objective and the training, and we'll talk about joint image distribution learning and the video distribution learning. Then we will then talk about computer vision applications, mostly on image-to-image translation. So introduction will also contain some small parts. We will talk about generative modeling and try to summarize recent generative models, put in perspective, and the Gaussian mixture models, probably the first model we learned from school. And we talk about manifold assumption, then variational autoencoders, and autoregressive models such as pixel CNN, and then the generative adversarial networks. We'll put them in a taxonomy. Okay. So generative modelings basically concern 2 business. One is density estimation. So you have a bunch of samples, and you want to learn a density function. So that's for new sample come, you can estimate the density. Another business is about sample generation. So you have a bunch of images, and you want to learn to synthesize new images with some characteristics similar to the images in your training data set. So it's mostly about this business. So we'll start with Gaussian mixture model. So it's quite simple. So assuming that we observe a set of samples, in this case, two-point clouds in a 2D plans. And to understand the samples, we can use generative modeling. Typically, what we do is we assume a parametric model. In this case, we can assume Gaussian mixture models. So in this model, we have a probability of X condition given theta. Theta is the model parameters. So in this case, the model parameters including the component contribution pi I, the mean, and the covariance matrices. So this is our inductive bias about how we're gonna interpret the data we observe. Now, this theta can be any arbitrary value. To learn the value that's relevant to our data set, we do model fitting. We do maximum likelihood learning. So basically given the data set, we want to find the parameter theta that can explain the observation well. And mostly, we'll assume the samples are gathered IID in an independent, identically distributed fashion. So we can decompose the data sets into individual sample sum and maximizing this sum of log likelihood function. From this approach, we learn the theta, and with this theta, we basically have our model. With this model, we can do density estimation. A new sample come, we can measure the density that this sample is coming from the distribution, and we can sample new points, like those points from the data sets. This is a very nice model, but it's probably only good for low-dimensional data. When dealing with high-dimensional data, such as images, it's kind of have difficulty in learning the distribution. In the high-dimensional space, things are far away, and most of the places are empty, so optimization could be a difficult problem. So to work with the high-dimensional data, we need something to help us. The most common assumption we use is the manifold assumption. It's basically saying that data lie approximately on a manifold of a much lower dimension than the input space. So if we have observed a bunch of data in high-dimensional space, we hypothesize we can unroll the structure into a nice 2D plane. So this is the assumption we're gonna be using to help us analyze high-dimensional data, such as images. And most of the generative model more or less use this assumption for layer modeling. So here are some examples of the manifolds. The left-hand side is a flat face manifold. So face images in this sample can be like 1,000 pixels. It's a high-dimensional data. But through manifold learning, we can map those faces into a two-dimensional space. In this case, the x-axis represents the pose. When you move along the x-axis, you change the pose of the faces, and the y-axis is expression. Different y coordinates give you a different expression of the subject. Another example is the MNIST example. It's a 784 dimensional data, but you can map them into a two-dimensional space, and you will see the digits are naturally clustered in certain area in the manifold. So you don't need to deal with high-dimensional data. With the manifold assumption, you can map them to a low-dimensional space. So one direct extension of apply Gaussian mixture model to model high-dimensional data is to use autoencoders. So it's a two-stage process. in the figure we see, here is the autoencoder. It has an encoder network E and a decoder network D. For an input image, we first use encoder E to map them to some latent code. Usually the latent code dimension is much smaller compared to the input image. And then we use the decoder network to reconstruct the image. So the autoencoder is trained by minimizing these Euclidean loss. We want to find the parameter, the network parameter E and D in order to successfully reconstruct the images. Once we have the encoder parameter, we can apply it to embed all the images into latent code. And we can apply Gaussian mixture model. And this way we can combine with the decoder, we can generate samples. So this is a very straightforward approach, very simple, but this is not end-to-end. So the distribution modeling and the encoding are two-stage process. So it's likely to be suboptimal. And it's often that the embeddings are still in high-dimensional space. So it's still difficult for a Gaussian mixture model to learn the distribution. And autoencoder has been criticized that it sometimes tend to memorize samples in the training set. So it means it's gonna have difficulty to generate some sample that we haven't seen before. So variational autoencoders more or less address this issue. So VAE, variational autoencoders, was kind of independently discovered by these two groups from Kimma Welding, published in iClear 2014, and from Verender, Mohammed, and Westra in the same year in ICML. So what they are doing is try to give a probabilistic interpretation of the latent code. So we want, try to embed the probability modeling in Gaussian mixture model into the autoencoder training part. So it's achieved by constrain the encoder to output a conditional Gaussian distribution. So Q theta is our encoding function, and it's a conditional distribution. So we want to find a latent code of Z condition on the input image Xj. And usually we model it as a normal distribution with the mean and the variance parameters. And the latent code is sampled from this conditional distribution. So the decoder then reconstruct the input images from samples drawn from the conditional distribution. So we sample a Z from this conditional distribution, and we apply the decoder network to reconstruct the image. And still, we want to do maximum likelihood learning, and VA is trying to do the same thing, but instead of directly maximize the log likelihood, they maximize the lower bound. The lower bound is like the following, which is basically you have the likelihood term, and you want the conditional distribution to be similar to a Gaussian, a normal Gaussian distribution with zero mean and unit variance. And it can be shown that this objective function, the sum of the minus scale divergent term plus the likelihood function, lower bound the likelihood term that we would like to maximize in the first place. So sampling is not a differentiable operation. So if you want to sample a latent code, you're gonna have to do something in order to use backpropagation, one of the most successful algorithms we know for training deep networks. So in their paper, they developed a trick called reparameterization trick, which effectively converts the sampling operation as an arithmetic operation, which is differentiable, so you can apply backpropagation to train the networks. So the variational distribution is given by Q theta, Z condition on X. And the sampling is then done by, you estimate the mean, and so it's like this. So you have an input image X, and you use the encoder network to estimate a mean vector and a vector of deviation, and you have U of X and the sigma of X. Then the sampling can be implemented by sample epsilon, which is from a standard normal distribution. You do an element-wise product here. So you have mu plus sigma times X, which give you the code Z. And through this process, you do the sampling, and this is differentiable. You basically just introduce additional variable epsilon, additional data epsilon, which you don't even need to backpropagate gradient to epsilon. So once you have the Z, you go through the decoder network, and you reconstruct the image. So VAE, because we can train with backpropagation, it's quite easy to train, but it tend to generate blurry images. So you can see on the left-hand side, we have the reconstructed faces, generated faces from the LFW datasets, and right-hand side we have the images, the models trained on the ImageNet, and we use the model, the image generated by this trained model. We can find that they tend to be blurry. So why are generated samples blurry? One explanation is that the pixel values are modeled as a conditional Gaussian, which leads to Euclidean loss minimization during training. And for this L2 loss, we know it had the problem of regress to the mean. And because it regress to the mean, you basically blur a couple of different versions together, so you have a blurry image. And also, I mean, these Euclidean loss has this like a non-ideal effect. But so far, it's difficult to handcraft a better objective function to produce sharp-looking images in this framework. But people are making progress. Maybe a few months later, we will see very sharp VAE images. And so here is just a slide where we try to illustrate the problem of Euclidean loss for image modeling. So in the figure, we can find that so there are two curves. Okay, the red curve is the Euclidean distance between these two image patches. You have a snowboarder, a jumping snowboarder, and a blue sky. So this red curve is their Euclidean distance between these two patches. The blue curve gives the Euclidean distance between the reference image and the translated version of this reference image. So you can see the snowboarder is shifted to the left. And for each shifted version, we compute the Euclidean loss. And we can find the Euclidean loss is actually larger than this version, comparing to a blue sky image. But intuitively, we will think that this translated version is more similar to the reference image. This tells us that Euclidean distance is not really a good metric for measuring the similarity between images. We might need to have a better metric. So this is about VAE. Another popular models for image generation is the autoregressive generative models. So for this high dimensional data, it's high dimensional structured data. We can choose an ordering. Each pixel has, we can give an index, and we can choose an ordering. With this ordering, we can factorize this, we can apply the product rule to factorize P of S into the products of conditional distribution. For each of the pixel, it condition on the pixel that's before it. And by applying this rule, we have a model for explaining the images. So it has some nice properties, including that P of S is tractable, easy to train, and easy to sample. It is a little bit slow because in the image generation, you have to generate pixel by pixels. But one of its drawbacks is that it doesn't have a latent representation. You don't see Z in this formulation. So currently the most popular autoregressive model is the pixel CNN model. It's by Aaron Vander Oud in 2016. So we see an image here where the order is based on horizontal scan, so x1 to Sn, and then the next row. So for generating this center pixel, it will condition on all of these blue pixels. And for this shape, this pixel that's this Si condition on is not a patch. It's irregular. So, but you can use a mask operation to implement this Xi condition on the previous pixel using a convolution neural network. And another thing is that since each time you try to predict one pixel value, and this we can use we can model this pixel value as a discrete variable, taking value from 0 to 255. So then it will become a classification problem. You can minimize the coarse entropy instead of minimizing the Euclidean loss. You can do this because each time you just need to deal with one pixel, so it's memory efficient. I mean, if you put you want to train a VAE for this for generate every pixel and use a discrete variable to model each pixel output, it cannot take a lot of memory space because each dimension you have a 255 times 3 possibilities. So, but you can do it in pixel CNNs. And image has 3 channels, R, G, and B. And with this autoregressive model, you can generate R pixel first, and then the generation of G condition on R, and generation of blue pixel condition on the red pixel and the green pixel. So this model kind of captures a lot of correlation within a patch. And it's kind of different to VAE, which is based on from the latent code directly to the image output. And with this discrete modeling of the pixel value, you can easily have a multimodal distribution. You have many different shapes, like this one, equal likely, but very likely for the 0 and 255, and this another shape. So this discrete variable also allow you these flexibilities. And these are some examples from the pixel CNN. Is the generation results from the CFA10. You can see that it generates image with like a natural capture the structure of a coral reef or hoses very well. And there's a recent work by Scott Reed published in ICMO 2017. So the aim is try to make pixel CNN faster. Currently, pixel CNN is generate the image pixel by pixel, but you can apply a multi-resolution approach, and then you can once you generate the first small resolution image, the other high resolution one you can generate them simultaneously, so it can be more efficient. And this multi-scale approach also help to provide better global structure. So here you can see that the bird, you can generate high resolution images, and it will capture the shape of the head of the bird. Okay, So this is the autoregressive model. Now we will be talking about generative adversarial networks. So it's from Goodfellow, published in NIPS 2014. So in GAN, it has two networks. We have a generator network G, and we have a discriminative network D. So, and there are two processing lines in this GAN training. The first one is you have an input image, which is sample from the data set, and you want is to output one. You want to say this is the real image. And for a sample, that is generated by mapping a random number, random vector to a synthetic image. The discriminator want to say it is a fake image, so it's output 0. Okay. So, in this framework, to determine if a generated content is like image or not, is the burden is shifted to the discriminator. You are using a classification approach to say this is a true image or fake images. We don't need to define any perceptual laws such as measuring the image similarity, and the discriminator will be doing the job. And I think GAN really get it very popular after the DC GAN paper, which the DC GAN paper is basically a nice implementation of GAN. So it's implement this generator network as a deep convolution network, starting with a 100-dimensional random vector sample either from uniform distribution or Gaussian distribution, and gradually computes representation in a higher spatial resolution, and eventually you have an output image. And once you have the GAN train, for each random number z, it mapped to a natural image. In this case, the GAN was trained to generate a bedroom and sample a number z. You have a bedroom, and then when you travel in the low-dimensional space, you can see the bedroom change from one bedroom to the other smoothly, and you can see example from other row of the images. So it's really nice. It's kind of convinces us that it's capture a very good, have a very good understanding of the images, and it also allow us to do vector space arithmetic. So basically, you have say that you have an image of a man with glasses. You can find the latent code Z. And for a man image without glasses, you can also find a latent code Z. And by also for woman image, you can find a latent code Z. And by subtract the latent code Z of a man with glasses by man and plus woman, you can generate, you can find a latent code Z that generates a woman with glasses. So it's allows us to do a arithmetic operation in the latent space to generate the content of interest. So, but GAN is different to VAE in one very crucial step. So in VAE, we have a decoder, which is more like an image generation function from Z to X. And we also have an encoder, kind of can be used to measure the likelihood. But in GAN, we only have the generation function. We don't have the, we don't actually model the density function. So there's nothing here. So it's kind of specialized for generation. And now we are ready to put these three models in perspective. Basically, they are all trying to do maximal likelihood learning. And for VAE and the PixelCN, they have explicit density function modeling. For PixelCN1, the density is tractable. But for VAE, you cannot directly compute the density, so you have to do approximation. For GAN, you don't directly model the density, but you have the generation function to synthesize new images. So this is a quick recap of what we talked about in the first part. We talk about generative modeling, major two tasks, density estimation, and the image generation. And we talk about the manifold assumption, that data live in low-dimensional space. And we talk about VAE, PSOCN, GANS, and the taxonomy. Okay, now we'll be talking about the GAN objective in more detail. So in this part, we'll first talk about the GAN objective. We'll talk about discriminator strategy and the GAN theory and the effects of limited discriminator capacity. So GAN is about solving a minimax problem. So you have an objective function like this. For a sample coming from the true data set, you want the D to provide a large log likelihood. For a sample coming from Z, from the random number, you want the synthesized image is put into the discriminator, and you want it to have a low likelihood. But when you so this is the objective, the discriminator. Of course, for the generator, you want it to produce image with high likelihood. So we will be using this notation throughout the presentation. So we use PGD to represent the model distribution, and G is usually modeled as a uniform or Gaussian random variable. So to solve this minimax problem, we usually do alternating gradient updates. So it consists of two steps. In the step one, we fix G, we fix the generator, and perform a gradient step to the discriminator, solving this optimization problem. So basically, you want the real sample to have high log likelihood, and for synthesized sample, you want to have low likelihood. And in the second step, you fix D, fix the discriminator, and perform a gradient step to the generator, solving this function, this optimization problem. You basically want to minimize this term. But in practice, instead of minimizing this 1 minus D of GD, we actually maximizing this log D of G of D. So it's basically saying that we want the synthesized image to have high log likelihood. So there's a difference between this. I mean, of course, this is different to the previous objective, and it turns out that the bottom one is a better objective function to maximize. We can understand this property from this figure. So the figure in the top is this objective function. It's basically have this shape, and because we want to minimize this objective function, and this objective function has no lower bound, so it frequently generates some numerical error or provides some instability. But when you try to maximize this function, it has a proper upper bound, so it will behave better. So the discriminator try to differentiate images from these two distributions, the model and the data. And we know the optimal discriminator is the base discriminator. Basically, if you have access to the density function, you just compute this ratio, and you know how often, which label to assign to this instance based on the base decision rule. So you can think of this as you have a data distribution, this black dot, and you have model distribution, the green curve, and the discriminator is basically estimate a decision boundary of this shape, and try to push the sample from the model distribution toward closer to the data distribution. And estimating this ratio using supervised learning through the discriminator network is the key approximation made in this GAN formulation. So here we are showing a figure, a video of training GAN to learn a Gaussian mixture model contains 3 components. So here you have the red points are samples coming from the true distribution, and the blue points are the samples coming from the current iteration of generative the model distribution, and it's initialized randomly. And from this figure, we can see that the model, what it does is quickly find a mode, but the shape of this blue dot it's not really a cloud. It's more like a degenerate version, more like a line. And it tries very hard to understand this cloud. And for many, many iterations, and gradually it was able to explore to other area. But it's kind of linking everything together, but suddenly it's come back to only discover 2 modes, and you keep trying, and eventually it will find the older modes in these examples. So in GAN, the theory is that the optimal discriminator is from this base decision rule. Basically, you measure the ratio of the sample, the density from the true distribution divided by the sum of the density from the true and the model distribution. And when we have an ideal discriminator, so your discriminator really approximates this optimal discriminator. What the generator does is to minimize the Jason-Shannon divergence between P of X and PG of Z, the data distribution and the model distribution. To satisfy this constraint, in addition to that D had to be an ideal discriminator, it also requires that D and G have sufficient capacity. And you also need to have a sufficiently large data set. And here's the expression of Jason-Shannon divergence. So you have P of S, PG of Z, and the KO divergence, it can be expressed as KO divergence to the mixture plus the KO divergence from the model distribution to the mixture. And the KO is represented as the expectation of this log ratio. But in practice, dataset size are always limited, and we only have finite network capacity. So we are just doing our best to approximate what we want to do. So recently, Sanjeev Arora has a paper in ICML 2017. They established the following theory for discriminator with capacity n, where n is the number of learnable parameters in the discriminator. The generator only need to remember C times n divided by epsilon squared times log n number of samples to be epsilon away from the optimal objective. So in practice, C is a very small number, and epsilon depends on how close you want to approximate your optimal objective. And so turns out that this term is not too big for regular for most of the case. So it means that the generator does not need to generalize. It only need to remember these amounts of sample. It can do a very good job to optimize the objective function. And even if you have a very large training data set, if your discriminator have limited capacity, there's not much you can do. So it actually shows that they show a very nice graph in their paper. In the x-axis, you have the size of discriminator. So it's basically the number of trainable parameters in the discriminator. And the y-axis is the diversity. And you can see that when the size of discriminator become large, you have more diversity. You basically was able to recover more from the data distribution. So here we quickly talk about the discriminator strategy, which is trying to implement this optimal based decision rule based on this ratio. And in the GAN theory, it try to, if your discriminator can is ideal, you are actually minimizing the Jason-Shannon divergence between the true distribution and the model distribution. But in practice, we have a limited capacity in the discriminator. So the diversity that the generator can, the diversity of samples that the generator can generate could be limited. Okay, so this is the second part. So now we come to GAN training. So GAN training, in this section, we will first talk about the non-convergence in GANs, and we'll talk about the mode class problem and the lack of global structure and some the tricks people use to train GANs, and new objective function people propose to train GANs, and surrogated objective function for training GANs, and network architecture for training GANs. Okay, so non-convergence in GANs. GAN training is theoretically guaranteed to converge if we can modify the density functions directly. But instead, we cannot directly modify the density function. What we have is the generation function G. It's not a density function. So instead, we just modify G. And we represent G and D as highly non-convex parametric function, deep networks. So because we really, we cannot do the ideal stuff we want to do, so and we do this approximation, so we have a, I mean, there's a lot of problem comes in. One of the problems is oscillation. We can train GAN for a very long time, generates a very many different categories of samples, keep changing different categories, keep changing different category, but not improving the image generation qualities. This is one problem frequently observed in GAN training. And another problem is mode clasp. So it means we cannot capture all the modes in the data distribution. We fail to generate certain type of samples. So we'll use this slide to illustrate the mode clasp problem. So in the top, we have the object function. So basically, this is V. You can think it's the objective function in GAN. We have two expectation term. So we want to maximize D, but also minimize G. But depends on the order we perform this optimization. It have a different effect. So if D is the inner loop, D is in the inner loop, D is the discriminator, we actually want to converge to correct distribution. But if G is in the inner loop, we try to generate some samples. Try to generate some samples that are very likely. Okay. So these two objectives not necessarily align with each other. So here we have a target. Target data distribution that we want to learn. It consists of a Gaussian clouds. It's a Gaussian mixture models. Each cloud have an equal weight, and we want to train again to learn this distribution. And we frequently observe this behavior. So it starts capturing one point cloud and jump to the other, and just keep changing the cloud it's captured, but never really converge to all the, to really never like capture the entire data distribution. Wasn't able to synthesize a different to learn these Gaussian clouds. So here is another analysis. So here we try to embed, try to project Gaussian cloud in low-dimensional space to high-dimensional space. So in this figure, we fix the data dimension to be, say, 512, and the data distribution, the data was original in a low-dimensional manifold, can be from two-dimensional vector space A32 to 128. So it's a manifold of different dimensions. We project Gaussian cloud in this low-dimensional manifold to this 512 high-dimensional space, and we apply GAN training to try to recover the distribution. We found that it has the following behavior. So this figure, the y-axis, measures the percentage of mode GAN was able to recover among A trials, and the x-axis represent the number of Gaussian clouds, number of modes in this low-dimensional the data distribution, which was generated in low-dimensional space and then randomly through a random projection project to a high-dimensional space. We found that it has this interesting behavior. So when the manifold dimension is fixed, okay, when you have more modes in the data distribution, the recovery rate decreases. So it means you have more modes, it has more difficulty in recover all the modes. And when the manifold dimension is larger, it also have difficulty in recovering the modes. So if we fix the number of modes in the distribution and just to analyze the behavior, the characteristic, like the dependency on data dimension and manifold dimension, we can find that the data dimension, the space you project your point to, really doesn't matter. What really matters is the manifold dimension. So if your data, the manifold, the data lies on is high dimensional, it becomes more difficult to recover the all the modes. And we know images is living in high dimensional space, but for different tasks, the manifold can have different dimensions. So for those tasks, as the manifold dimension is larger, we will experience some difficulty in recovering all the modes. So this is previously it's about mode clasping. Here is even for those modes we were able to recover, we still have certain problems. Usually the generated images kind of lack global structure. For example, this is supposed to be a dog, but it's if you look local patches, it's really like a patches from a dog images. But if you look at entire image, it doesn't really look like a dog. And I don't know what is this, but this, and this is probably a cat. So it still lack global structure. By the way, this is the generation model trained on ImageNet dataset. So it also have problem with counting. For example, we have monkeys with 3 heads and many eyes, and I think this is probably a dog with 3 heads. So again, locally it could look like a real image, but globally it doesn't. It does not. So this is one of the problems. So because GAN training can generate sharp images, people feel like it's a good direction to go to generate realistic images. But currently it has a couple of problems as mentioned. So to address these problems, people with different background try to approach this problem in different ways. So here I try to summarize what happened during maybe just 1 year. for improving GAN training under 4 different categories. So this is based on my categorization. I think other way to categorize these works exist, but I will just describe my way. So I divide them into tricks, new objectives, surrogated or auxiliary objective, and network architecture. So by using trick, we can improve GAN training. By using new objective function, we may can improve GAN training, or using auxiliary objective function, or change the network architecture. So there are many other works. I have, but we cannot cover all of them. So I'll just limit myself to these. I think already many. So we'll start with tricks. One trick people use is called one-sided label smoothing. Was used in the improved GAN paper by from OpenAI, published in NIPS last year. So what it does is that instead of assume the true label, you assign like a probability 1 to actually it's kind of try to make the discriminator less certain about its prediction. So replace the 1 in the original GAN objective function with 0.9. So it kind of has the effects of it does not reduce the classification accuracy, but only confidence. It also prevents discriminator from giving very large gradient signal to the generator. And but sometimes it prevents extrapolating. So it kind of prevents extrapolating to encourage extreme samples. Some people use different label smoothing scheme. One is two-side, means not only change the label for the true sample, you also change the label for fake samples. And Sumi compose a list in this website, so you are welcome to check out the website to see like other tricks that people use. And another trick people use is the historical generator badges, which is used in Apple's GAN paper. So what it does is that the discriminator is updated not only based on the current batch generated by the generator as this iteration, it also updated by the previous batches, like from the previous iteration. So your discriminator had to classify real sample as 1, and for the current batch, it had to be 0, and for the previous batch, it had to be 0, and depends on how many you want to use. So you have a bunch of batches. And this historical batch has been found helpful in stabilize the discriminator training in the early stage. In the later stage, if your generator converges to the true one, converges, then the historical batches will be pretty much the current batches. So it does not affect the objective function. And there are other tricks, as I mentioned earlier, you can find from Sumi's website. For example, you can use labels for training. You can should normalize the input to -1 to 1, use hyperbolic tension, use Bechdel, and avoid sparse gradient. Don't use ReLU, maybe use leaky ReLU or parameter ReLU. Don't use mass pooling. And in OpenAI's improved GAN paper, they propose virtual Bechdel or another mini batch discrimination. Just to give you a flavor that different tricks has been used to improve GAN training. The other category of works focusing on proposing new objective functions. The EBGAN, LSGAN, WGAN, BEGAN, FGAN. So EBGAN is from Zhao, Medu, and LeCun, published in iClear 2017. So here we see the original GAN network, discriminator and generator. In the EBGAN, energy-based generative adversarial network, they replace the discriminator by an energy function. And for image sample from the dataset, for the true image, you want it to have a low energy. And for image coming from the generator network, you want it to have a high energy. And usually the energy function is implemented as an autoencoder, and the energy value is the reconstruction error. So basically you want to train an autoencoder which can perfectly reconstruct real images, but not so well in fake images. And the generator is then motivated to generate some images that can be well reconstructed by the autoencoder, and hence it will be closer to the real images. So this is the objective function. So the energy is given by the reconstruction loss. Apply encoder, decoder, and then subtract the input image. And the objective of the discriminator is to have a low energy for real image and high energy for a sample coming from the generator. And the use m, which is a constant, try to upbound the energies. And the generator objective is purely just want to minimize the energy. Try to generate a sample that the autoencoder can perfectly reconstruct. And these are the images from their paper. You can see this from the LSUM. It kind of generates many different versions, quite realistic compared to the DC GAN paper. So another objective function that people suggest for GAN training is the LS GAN. It's called D-square Generative Adversarial Network. So, in the original GAN formulation, we try to use cross entropy loss. In LS GAN, we try to use D-square loss. So here, in original GAN, you want to maximize this. Okay, we'll be using minimization. We want to minimize this negative log likelihood for real images, and for synthetic one, we try to minimize minus log 1 minus d of GD. In LS GAN, instead you want the discriminator to produce 1 for real images and 0 for fake images. In the D-square, try to minimize in the Euclidean, try to minimize this Euclidean distance. The generator in GAN is to kind of minimize this negative log likelihood, but for LS GAN, you try to make the D produce 1. It has, I mean, in original GAN, it's still try to produce 1 and 0. You know, LS GAN is also 1 to 0, but just the objective function is different. They have different characteristic. And in LS GAN paper, they find out that when you minimize this square loss, it's actually minimize a different distance between the two distributions. So in GAN, we know it's minimizing the Jason-Shannon divergence between the data distribution and the model distribution given in this form. But when you do LS GAN, it's kind of minimizing the chi-square distance between the mixture distribution and the PG. So you try to minimize the chi-square distance between these two distributions. So in this case, one of the target distribution is actually a mixture of the generator distribution and the true data distribution. And it was reported that it provide more stability in GAN training. So they generate very high resolution, sharp looking images. Probably one of the best looking images for these LSUM data sets. Another objective function people propose is the Wasserstein GAN. So it's from Ajovsky, Chintala, and Botu, called Wasserstein GAN. Here they try to replace the mechanically speaking, they replace the classifier where the classifier try to produce something 0 or 1 with a critic function. So it means it's a value, a real number. It can be anything. So what they want to do is for sample from the data sets, you want to have a high critic value. And for sample from the generator, G of Z, you want to have a low critic value. And when training the generator, you want to do the opposite. You want to train the G such that it can produce an image. The critic will assign high value to the image. So it was shown in the WGAN paper that instead of when you do WGAN, when you minimizing when you train okay, in the original GAN, again we are minimizing the Josephson divergence between the data distribution and model distribution. But when doing WGAN, you're trying to minimize the Earth mover distance between P of S and P of G of D. So it's given in this form. So you have two distribution, and you want to find a joint distribution. It's more like a mapping between these sample from these two distribution. You want to search for a mapping such that you can align a sample from this distribution and the model distribution in this L2 sense. So the paper produced quite nice results on the indocing. So they try to motivate why this Earth mover distance is better than the Josephson divergence. And the example they use is this one. So here, the black curve is the GAN manifold, the curve manifold you learn in your generator. And the red one is the target, the data manifold. So we will be run into this small area, the blue one, where we find that we have two straight lines here. Okay, so as soon as we can directly control the shape here, theta. So now we measure the Josephson divergence between these two distributions. We found that the Josephson divergence values for different theta is as shown in this figure. It is 0 when the theta is 0, and it will be log 2 every other place. So when you are moving towards 0, even though you are making progress, it does not reflect on your Josephson divergence. But if you do Earth mover distance, you found that the distance is kind of proportional to how close you are toward the true target. So you can measure your progress. And that's one argument they make in the paper why we should prefer WGAN over GAN. So just put them together. You can see that this is a much nicer function to use because it shows you the progress. But it's based on if we can directly change the density shape parameter. If we can do that, the Earth mover distance is smooth. But again, we do not directly change the density shape. What we have control is the generation function. We train neural network to and change the parameter in G. So the benefits shown in this figure may not fully represent in GAN training. So recently there's another paper from Google. It's called Boundary Equilibrium GAN. It's called BE-GAN by Bernauer, Schumann, and Metz. So BE-GAN is based on EB-GAN. So EB-GAN, let me remind you again, it's an energy-based GAN. BE-GAN is boundary equilibrium GAN. So in EB-GAN, we replace the discriminator with an energy function and want to assign low energy value to input image, to true image, and high energy value to generated image. So BE-GAN used the same architecture, but now instead of minimizing the distance between the two distributions, the data distribution and the model distribution, it tried to minimize the distance between the energy value distribution for true samples and the energy value distribution for fake samples. They are not minimizing distance between images distributions. They are minimizing the distance between energy value distribution from these two distributions, this energy value. And they are not directly minimizing the distance. Okay, I should first say that the way they measure the distance between the two distributions is based on what's the stand one, which is the Earth movement distance, similar to WGAN, but it's different to WGAN because they are minimizing the energy value distribution, not image distribution. So, and instead of minimizing the Earth movement distance directly, they minimize a low bound of the Earth movement distance. So this is the Earth movement distance from this is WGAN formulation, where the PS and PG are the image distribution. In BGAN, you are minimizing the energy value distribution, not the image distribution. And for this term, you can actually bound it below. You can take the absolute value out from the expectation and low bound this objective value. And when you further express this turnout, you basically have the mean energy value from the true data of the true image minus the mean energy value from synthetic image. And this is the final objective function. So the key point is it's not minimizing the image distribution, it's the energy distribution. And they have one very interesting way of doing that, which they borrow from control theory. They try to use so here we have the energy terms from the true distribution and fake distribution, right? So here they add a KT here, try to control the balance between these two goals when you train the discriminator. But when you train the generator, you don't have KT because all you care about is the generator. And this KT is updated through this equation, where gamma is a constant, is a hyperparameter, which you determine beforehand, usually between value between 0 and 1. So you fix this one, and this is more like your error. And based on this error, you kind of feedback to this K, and which they show that it help stabilize GAN training. And they generate very good like face images. They compare to EBGAN and seem to be produce sharper face images. So what we talk about, so there's others I couldn't include in this tutorial, but what we talk about so far are the new objective people propose to train GANs. Okay, next we will be talk about the surrogate and auxiliary objective function, including unroll GAN, WGAN GP, and Dragon. So in the GAN formulation, you actually want to update the you want to train the you want to update the generator based on the optimal discriminator, which means that you have to ideally you have to keep update the discriminator, performing many iterations. So in unroll GAN, they propose a different idea, where instead of using the one iteration of discriminator to update the generator, they unroll the update process of the discriminator. So you have a sequence of the discriminator. One is derived from the other, and you use these discriminators to update your generator. So it's kind of predicting what the using what the discriminator might do relating to your change to help you better change your generation function. But you and that's the way how they update the generator. But for update the discriminator, they use the same way. Just use the current generator to update the discriminator. But for updating the generator, you use unrolled versions of the discriminator, many of them together to update the generator. And it has been shown to have the property of avoid the generator to generate samples from few modes. So this is their objective function when training the generator. So instead of D, they use DK, which is DK is derived from the current discriminator and the generator. It's unrolled version. So you have many of them. And consider several feature update of the discriminator as updated generator. So they compare this unrolled GAN to GAN training and show that for this Gaussian cloud cases we talked earlier, it is able to capture all the modes. But when you just use GAN, it was not, it's only oscillates between different modes. So the WGAN GP is a recent paper, a very recent paper. It's based on WGAN, but it's proposed to add a list term, which regularize the gradient of the discriminator on these Y samples, where Y here is interpolation between a sample from X, which is the true images, and GG, which is the synthesized image. So basically, you sample a true image, and you synthesize another a generated image, and you sample a uniform random number between 0 and 1, and you do the mixture of these two images, which give you the Y, which is the imaginary sample. For these samples, you want is to have a gradient norm equal close to 1. They do this because through their analysis, they found that the optimal critic has the union gradient norm almost everywhere. And they show that by using this OCD objective function, it's help you to stabilize GAN training. So here you don't see the benefits, but in their paper they show that when you remove batch norm from the generator, the WGAN GP can still produce good-looking images, but the other method failed. So a similar idea, but not identical, a similar idea was proposed by this Dragon paper. But instead of working with the WGAN objective, they work on the original GAN objective function, where the D is discriminator, and you are based on minimizing the Jessen-Shannon divergence. What they do is they also add this auxiliary objective function where you want to regularize the gradient norm for this Y sample to make it close to 1. But this Y sample is sampled differently. In the previously, in the WGAN GP, you sample a true sample and a synthesized sample and do the blending. Here you sample a true sample and another deviation, small number sigma, and you blend in this true sample with a deviated version of this sample. So they have a theory showing why this is helpful. So it's also shown this kind of a trick that's used in original mini-mass problem. So this is about the auxiliary objective. And another thing people do to improve GAN training is to change the network architecture. Here we have a Laplace GAN. So it's based on the image pyramid idea. So you will go from right to left. So basically you have a G3 generator that converts a random vector to a small resolution image. And you upsample the image. And this upsampled image and another random number Z2 together fit into G2, which produce a residual of the images. And this residual is added to this upsampled version to create a higher resolution image. And this one is again upsample again, go to the next generator and to generate a residual in higher resolution. You keep on doing that until you have a very high resolution image. So instead of using the DC GAN styled network, they bring the idea from computer vision and design a like image pyramid like network to generate high resolution images. They were able to show that they make progress for each iterations. And to train the Lapa GAN, you can train each resolution separately. For small resolution, you synthesize an image and have a discriminator differentiate, synthesize one and real true one. But for higher resolution, you use the real image to produce the low resolution one, and then compute the residual, which will be the true sample, and use G2 to produce residual based on the low resolution image and G2, and have this discriminator differentiate if the residual looks like a real residual. And so you can train, so the training here does not depend on the previous one, so you can train everything independently. So evaluation is a big problem in GAN training. So currently there are two very popular ways. One is based on inception loss. Basically, you train an accurate classifier, and you then train a conditional image generation model. So it's basically say that you know what class of image you're gonna generate, and now use this classifier to verify if the classifier recognizes the image you generate as the class you want to generate. So it's kind of evaluate how much control you have in the generated content. But it does not say that the generated image will lose real. It's only said the generated image will be classified as you will decide the class by the classifier. And probably the most popular approach is human evaluation. So you ask a human subject to compare the image qualities. So generative models are difficult to evaluate, and it's pointed out in the one of the ICLEAR 2016 paper. For example, for human evaluation, if you just show the human viewer some random, so if your generator just remember a few images, and you keep remember few true images, so it can generate these few images from the training data set. It doesn't generalize. But when you show this image to human viewer, they will think that it's very realistic. But it does not say that your generator really learned the data distribution. So basically, for most of the metrics, you can hack them. And so still an open problem, and it's probably the reason why we have so many different ways of training GANs. We're still looking for a proper metric to compare different models. So I know it's quite long, but it's end of the first part. And Julie gonna give us some demo, and after the demo, we will take a 30-minute break, and then we come back to the joint image distribution and video distribution and the computer vision applications. Oh, any questions? Yes, please. Yes. The slides will be uploaded to my GitHub website before midnight tonight. So I will be. Okay. You have this one.
sorry, it's going to take some time to set up. If you have other questions or if you want to stretch your legs, feel free for 5 minutes. Sorry about that. Sorry? No. We're going to tell already. So ask Minu. Minu's here. I can tell you. Okay. Okay, so I'm the interlude. Basically, what I'm going to try to do in that 20 minutes, 30 minutes is I'm going to show why you should care about what Minu told you. It gave you that long list of different hacks and tricks and techniques. And I mean, there are a lot of them. And the first time you're going to train your GAN, basically, it can be a little daunting to know which one you're going to choose. And what I'm going to do is I'm going to share my experience through GAN training we did, where it got super funny because we basically didn't anticipate to see the problems we've seen and how we overcome that problem. So when Minu talked about oscillation, what does an oscillation look like? When we talk about having problem making images bigger, what happens? Whether you can bootstrap again. If you started pre-training, what happens? So the first example is going to be a very simple example. Last year, I got very fond of the DC GAN paper. I thought the idea was like extremely interesting. And so as a company, we decided to showcase that paper at our GPU Technology Conference keynote. But between archive and actually showcasing that paper, we went through interesting stories, and that's what I'm going to try to share with you. And the second one is we also started to do a lab to teach students how to do photo editing with GANs. And again, some things are very interesting and very easy to comprehend, but some other need a little bit work, and that's what I'm going to try to show. So the first one is the DC GAN. So Minu presented DC GAN, and that's the GTC demo we ran last year. So basically what we wanted to do is, before it was cool, we wanted to generate a painting that was looking like a painting. So we took 20K images of Victorian paintings. So of course we didn't have 20K images because the Victorian period was long, but it's not that long. So it was a long augmentation phase. And we tried to have the computer paint its own pictures using simple guidelines, or using, trying to understand the features of the GAN and understand the features of those Victorian paintings. So luckily, that's what the result is. I'm going to show you that demo after. But I'm going to guide you through the process we use to do that. So first is the paper. So this is the DC GAN paper. So from Alec Radford, Luc Smith, and Sumit Dishitala. And what I like very much about that paper is that it was a breakthrough for me because they use CNN in a very, very nice way. They use batch norm. They were relatively tricky on the way they use batch norm. And it was one of the, at least first DLCV paper that I was reading that contains like very interesting, squares with a bunch of tricks in it. So initially I was like, oh yeah, that looks nice. Like they figured out how to put that in practice. That shouldn't be so hard. I was very wrong. So just the instruction to DC GAN, we like very much to explain that very simply. So I like very much Jan's course path. I wanted to share that. And just to remember, for everybody to remember, it's a very simple structure for DC GAN. You have the generator, you have the discriminator. Both are CNNs. They are the same CNNs. You got your log likelihood, and then you can just generate whatever image you want. So this is what the structure looks like. So if you've been doing deep learning, it's a relatively shallow network. It's not too big, right? I just want to attract your attention, though, to the fact that the size of the image you're going to be generating is actually the size of the last layer, right? So relatively simple, small CNN, two CNN to train at the same time. Sure, shouldn't be a big deal. The good thing is also they had the code available. It was a torch implementation. The torch implementation is extremely simple to read and modify. So you have like mini batches. You had the batch size. That's what the generator looks like. So that's what the first network is. And basically, the discriminator is exactly the same code, the other way around. So yes, I did what everybody tells not to do to the student, never show code on the slide. I did. I'm going to do it again. The reason I'm going to do that is because the loss is very simple. That's basically what the code looks like. But behind those like maybe 70 lines of code total, there is a lot of things that are happening and that are very difficult to master. So we had constraints. The screen we were going to use were like basically a gigantic 4K screen. The DC GAN paper is 64 by 64. All those images are 64 by 64. That's extremely small. So we wanted to have something that was slightly bigger. So we said, oh, how about we try 128 by 28? That shouldn't be so hard. That was our first mistake. The original paper uses the cell bay faces and the Elson room faces. It was relatively unfit for a demo for us. Everybody's doing vision here. When you see a face, and if the face is not perfect, every human, and we're going to go back to human evaluation, every human is going to recognize the face is not perfect. It's very easy to recognize zombies. So basically, we couldn't be coming with a demo that was just showing a bunch of zombies, like Ming, you have shown that, people with 3 eyes, like, teeth that were in their ears, and so on and so forth. If you've been playing with this on face data set, that's what you're going to get when you have training problem. And we needed a data set, which is not so easy. So we still had that Victorian image ID, so we pushed that one. And I'm going to discuss how we had to kind of like play tricks on that data set to make that work. So, okay, so it's easy. We just need to double the size of the image, right? So we just need to change the network, double the size of the last layer, and then propagate that to the rest of the network, which in terms of code is relatively simple. Oh, sorry, I forgot to do that. It's relatively simple, right? We're just here. We just had another layer, and we go on and so forth, and we just have the same network that triggers images that are double the size. The little teeny tiny problem is that our network is then almost double the size too. So the training is not going to go as well. And that's exactly what happened. We started training, and it was extremely hard to train. And the best we could do was this. That was extremely disappointing. So that was our first, real experience with 128 by 128, so we had to do something. We go back to the paper and say the paper mentioned upscaling. You try upscaling. That's what happens when you do upscaling on the Elson data set. You end up with something in the middle. This is supposed to, I think it was a bedroom. And then on the other side, you have fog, because you cannot scale from the network. So that was not an option too. So we also wanted to show what we thought was a very, very interesting point in terms of vision of the paper, is that you could do feature combination and you could do arithmetics on the feature, which was very cool. So that's the end result we got. And basically what we wanted to do is, the first column on the left is we wanted to take a sunset that had like a bad weather. We wanted to remove the clouds that are in the middle, and we wanted to add the beach so that we could get a sunset at the beach. That took a long, long time. Like, that picture was a big Ori moment. I'm going to try to show you why. So, interestingly, Ming, you mentioned that there's a known limitation in GANs, is you still have to resort to human evaluation when you train. And the reason is, and you can't only just like kick up like, 100 gazillion training and come back later on and look at it, because you might miss something. The problem is not only you have to go to human evaluation, but like every network training, you want to know how it goes with time, how it goes with different iterations and so on. And so basically you need human evaluation, but almost at every stage in a process, which makes it extremely daunting. This is an example of what happens. So the red arrow shows that the training is not going well. Can anybody tell me why? Yes? Yes, the answer was repeated structure. I got repeated structures. So what's going wrong? Why can I get repeated structures? Sorry? Overfitting. Kind of. It's one form. So basically, what's going right here is I got a combination of registration problem and oscillation problems. Remember, I said I had to augment my data set. I did augment my data set relatively stupidly, right? Shifting, flipping. Plus, those networks are made so that they have the size of the image. So they have problem registering the images at the right size. Plus they have to, they sometimes when you train, they oscillate. And that's exactly what's going on here. You can feel that the networks wants to do a forest, which is made of a bunch of trunks. But since I augmented very much and I don't have that much data, the image is going to keep on shifting. Plus it's oscillating, so the network cannot find what the right registration mechanism is. However, the reason I still want to keep that one, for most of the other image, I'm in a pretty good spot. So basically, I want to use that point at another, I want to take that one, make a snapshot, and use that to bootstrap. Maybe by removing the forest, if they have registration problems. And that's basically what's happening here. This is only to show why it's important to use human evaluation at every stage of the process. Hopefully, it won't be needed so much, but so far, we're still limited in doing that. Okay. So there's a lot of tricks that say, oh, yeah, so if you can't train, the problem might be your gradient descent mechanism. That's usually the first reflex we have. When it doesn't train, okay, let's change your learning rate, let's change the gradient technique, yeah, let's find something. And so we had results that were extremely different depending on the random scene we were using. So we had some kind of bug in our initialization implementation. And the gradient descent technique, what would happen is it would train, and then it would completely collapse. And so basically, the solution is to use ADAM to work. It's very well explained in the paper, actually. Work on beta 1 and beta 2, but also sometimes stop the training and change completely your gradient descent technique when you know you're in a good spot, which is a little bit cheating, actually, because it means we might be in a local minima and we might be oversampling that local minima. But in practice, it worked a little bit. Okay, so then I've shown you at the beginning that I was not training, and I showed you images where I finally managed to train. And so when we saw that it was oscillating and we couldn't get anything, the classical idea we have is, okay, let's bootstrap. Okay, usually you bootstrap with something and it's going to work, but we didn't have anything to bootstrap. So we tried to resort to lab GAN, for example, where we would increase the size by changing the structure of the network. It didn't work either. So at this big moment of despair, what you do is you go back to the paper. And the paper has this interesting paragraph, which is here, where they talk about extraction pipeline using k-means. So basically, we realized that why we were having problems is because our data was very, very diverse. And what we could do, since eventually a GAN can be seen as a big unsupervised training technique, was just pre-cluster the data we have. And so we actually pre-clustered most of the data, and we started pushing categories one by one to initialize the training correctly. And that worked. And I say you can bootstrap. So we wanted to train Kincaids. So those on the left, for those, you know, if you're not from the US, for me, maybe you didn't know Kincaids. I didn't know Kincaids before that experiment. And people say, oh, you should generate Kincaids. Like, there's a Kincaid in every model when we travel. And I was like, okay, let's try to do Kincaids. And then Kincaids didn't work very well because they often have a lot of trees and they suffer very much from that registration problem. So what we did, we actually bootstrapped Kincaid with Victorian images, and actually you can generate a whole class of Victorian Kincaid just by looking what happens to the whole gradient descent. And you can decide how much Victorian, how much Kincaid you want by just pushing the images along the way. That was very fun. Okay, so now I'm going to show you what it looks like. So this is basically the training happening. So I started at a point where I started reaching somewhere where we could see images. So this is the images that I'm pushing through the network. And this is the state the network is in. So while we pre-clustered the images, what we did so that the network would train is we had images that were like in 10 categories. And to kickstart the training, we started the training with 3 categories, and then added 2 categories, then having 7 categories, which kind of defeats the purpose of a GAN training, because in theory, it's an unsupervised technique, so we use like semi-supervised, but that's basically where we were. And then, so that should start. I'm sorry, that's the demo effect. Okay, here we go. And so those are the kind of images we can generate. So we can generate a landscape, we can generate a prairie, we can easily generate like a sunset at the beach, and then what I'm going to show you is basically the arithmetic with it, and that's basically the bad weather sunset, the clouds, the beach, and how we obtain the sunset at the beach. That's the whole demo in short. So the conclusion of that is the paper was very cool. It was great. We had a lot of fun. However, all the tips and tricks are really, really needed, even to train something which is as simple as that. I'm pretty sure, like, from what Ming you've shown, is the most basic technique ever. However, it's still very difficult to train. Any question on that before I move to the second one? Yes? A TSNE. The TSNE, or like, you have 2 ways to do that. So the question was, how do you cluster your training data? So all tricks are allowed. So you could do TSNE. Another trick which works very well, which is kind of lame, is you could also do information retrieval. Like on Victorian paintings, if you use, for example, the VGG annotation, you can say, hey, can you retrieve to me all the boats? And if you retrieve to me all the boats on the Victorian paintings, you obtain those like seas with the boat on there and the cliff and everything. And the data set is, I mean, I would say so naturally well conditioned that it ends up being pre-clustered. So there are a lot of tricks. For bootstrapping, you know, everything's a little, whatever works. Any other question? Yeah. That's a very good point. So the question was, you mentioned we tried LabGAN, and there was this new thing in the Wasserstein paper. At the time, the Wasserstein paper was not out. And you're right. The thing to do is actually to look at that. So basically, this is just to show the beginning of the process. But yes, LabGAN didn't work. It didn't train. The next step is to go Wasserstein GAN. And actually, if you do energy-based in any fashion, that means you should be good to go. It doesn't mean it's going to train well, and you still have to. It doesn't mean it's going to train easily, and you won't have to resort so much to clustering tricks or gradient descent tricks. But at least it should be better conditioned overall. Yes. They argue that you don't need so much image supervision. Honestly, I haven't tried on that data set, but yes, it should make the process better. This contains a lot of human supervision. Any other question? Okay, next one. Photo editing with GANs. So for those of you that went downstairs at the expo floor yesterday on the booth, you might have seen a demo when we train a GAN on celebrity faces. And I'm just going to show you the whole process. And actually, what I want to show you is what happened in the latent space when we basically oscillate on the Z parameter in DC GAN. So this is just to remind everybody about how we do it. This is in a G space, a man plus blonde hair, blue eyes, and so on, and how you go from one to the other by just playing on the features. Minu's going to explain that more afterwards, I think. So I'm kind of spoiling it, so I'm just going to pass very, very quickly. But that's basically the idea. Again, classical structure, except we're going to have the encoder, and we're going to try to see what happens. Because we need those features to be labeled, right? In the previous example I had, I told you it was a beach, I told you it was a forest, but the question I had is how do you pre-cluster? So if you don't have those features already defined in any way, then you can't have that. So you can actually condition with the feature now, and you don't have to do that manually. So here is what happened when you visualize the generator. And these are the attributes. Again, I'm going to pass quickly because Ming mentioned that. But what's super funny is we can actually play with the attributes. So when you have a bunch of people, blonde hair, dark hair, and glasses, and you can make people more male, make people more female, make people smiling, make people attractive. What is very funny is we started showcasing that demo early this year, and the first thing that people would come and see us were they would come to the booth and they would try, and they would put the mustache slider up to the right, and they would put female on top. And it didn't work. And it was actually super funny because it showed that even if you have a latent space, if you don't have information in that latent space, there's no way you can invent it. You can generate, but you cannot invent. And so basically, one has to be very careful with those training and playing on the latent space, because if you don't have the data, you don't have the data. So while I can generate a man with glasses, if I didn't have so many, I will not be able to generate a man with a mustache. So that's the limit. If you don't have the data initially, you might have the good features. It might just be that you might not be able to sample enough the latent space. We can also extract attributes. So we can take a picture of somebody and see which are the features that are the more associated to that image, which is sometimes interesting. And we need to be very careful when we train, in particular after conversion. We need to stop updating the discriminator, because we could start refining too much and unbalancing the process, especially when we work with features. And those are basically the zombies I was talking about before. Luckily, those have only 2 eyes. What is super nice is to go back and visualize the data set, especially in 3D. Once you have those latent features and so on, you can see. So this is a static image in the slide. But if you were to look at that with an app, you would see that some parts of the space are less densely populated. And it's basically the reason why, yes, you won't have a woman with a mustache, but you can see the people that have the glasses and so on are overall in the same area in a latent space when you project it. Okay, if you want to read more about that, we get a blog post that explains everything. And because I'm not going to detail it completely. And we also have a way for you to train it and do that, and do the conditioning on MNIST, and also train and do the face demonstration I've shown you before. I'll take any question you want. And I guess after the question, we'll take a break. Questions? Okay, thank you very much.
Hello. Welcome back to the tutorial. It's gonna be the second half. Before we start, I want to show this website. I just uploaded the tutorial slides to this GitHub website. So you can click on slides, you can download the tutorial, the slides. If I made any updates, I will sync with this repository. So I'll be giving the rest about 1.5 hours of slides, and I found that as I speak, my energy level decrease, and sometimes sometimes some sentence may not make a lot of sense. If it does, just let me know. I'll try to explain it again. Yeah. So do this. So actually, it's already available. You can take a picture. Okay, so this is gonna be the second part. We will be talking about two things. One is joint image distribution and video distribution learning. And then we'll talk about computer vision applications, mostly on image translation, supervised and unsupervised. So joint image distribution and video distribution learning. So in this part, typical joint image distribution learning followed by video distribution learning. Okay, sorry. Okay, so before we start, we need to define what is the joint distribution of multi-domain images. So imagine you have a scene, you have a space, you have two cubes, and you have a camera. You take a picture of the scene, you have an image. Depends on the sensor you use, you have an image of different modality. If you use a CMOS sensor, you get a color image. Use a thermal sensor, you get thermal images. And if you use a depth sensor, you get depth images. So naturally, for natural scenes, there's a joint distribution of multi-domain images. That's our target. We want to learn this distribution. So this is a formulation. So we will use X for different domain. So what we want to learn is this joint distribution, say X color, X thermal, X depth. And we will be using modality and domain interchangeably in this presentation. So modality means domain here. So you can also define domain by attribute, like a face with smiling attribute or a face without smiling attribute, with beard, no beard, young, senior, different font, image drawing, the same place in different weather. So you can define joint distribution of multi-domain images in many ways, and you can define it in an abstract level. So if you have a data set where you have, say, corresponding image. What do I mean by corresponding images? You have a color image of a scene. You also have a depth image of the scene taken from the same camera at the same location. Or you have a person smile and a person in the neutral face. If you have the, or another example is you have a winter and summer image. Okay, so under this supervised setting or paired with access to pair the images in the training data set, you can easily extend the original GAN framework for learning the joint distribution. So here, the joint distribution, again, we want to learn the P of X, image from the first domain and X image from the second domain. So again, we have a discriminator trying to differentiate real image, and generator generates some image, and the discriminator differentiates true or fake. To extend to multi-domain, all you need to do, because you have corresponding images, all you need to do is to concat those images in the channels. So instead of 3-dimensional, it's become 6-dimensional. And your generator map a random vector to a 6-dimensional images, and you can split them into 2 halves. And this way you can learn joint distribution. Very simple extension to image of multi-domains, distribution of multi-domain images. But the more interesting case is what happens if we don't have paired images. To capture corresponding images, sometimes it could be costly. For winter and summer, you have to set up camera, remember the place, and take it again, like a half year later. For some attribute, you have physically alter the appearance of human. Say you want to color the hair. So this can be quite cumbersome. So then it motivates you actually want to figure out a way to learn the joint distribution, but using samples from marginal distribution. You only have a distribution from the first domain. You just have some image from the first domain, some summertime images, and another set of images like some wintertime images. You don't have correlation, but you want to learn to model joint distribution of these 2 modalities. So we published a paper in last year's NIPS showing that this is possible with a GAN framework, which we call coupled generative adversarial networks. So in this paper, we show that you can learn a joint distribution of images using samples from the marginal distribution. So in theory, this is not possible because there are for 2 marginal distribution, there are infinite many joint distribution. Where you marginalize them, you get your marginal distribution. But in the image domains, we can use some other prior we have about the images, and to help us design a network that it will encourage learning the joint distribution from the marginal samples from the marginal distributions. Okay, so what we can do, very simple, as shown in this paper, is the GAN paper, is that okay, now we have to learn this joint distribution in this unsupervised setting, we need to use more networks. So here we will have 4 networks. We have a discriminator for domain 1, discriminator for domain 2. We have a generator for domain 1 and a generator for domain 2. Okay, so discriminator in domain 1 try to differentiate summertime images versus true summertime images versus synthesized summertime images. Discriminator in domain 2 differentiates real winter images over fake winter images. And the 2 generator here take a random number z and generate a pair of images. And for the image coming out from generator 1, you want it to look like summertime images. For generator coming from the wintertime, you want to look like a wintertime image. So because we know that image of different modality, they describe the same high-level concepts. For example, I take a picture of the scene. I know it's a bunch of audience. It's a conference center. It's a ballroom. So you can use the same high-level description to describe a color image and a depth image. So because you can use the same high-level description to describe the same thing, it means it makes sense to share their high-level weights. What I mean is, if we if we buy the assumption that deep network learn a hierarchical features from low resolution to high resolution, the higher level actually capture the more global concepts. Then to describe the color and depth images, it should come from the same high level concepts. And then eventually in the low level parts, it will be implemented as like a color as a color image or depth images. Just low level can be different. High level is the same. So we found that by implementing this idea through the weight sharing constraints, even though in the training set you don't have paired data, eventually you will be able to generate pair of corresponding images. Think about it. So the goal of the generator is to defeat the discriminator, right? When we share the weight, it's limiting the capacity. So each of the generator will has less capability in defeating the discriminator if they don't collaborate. If I want to use the same high-level concept to explain two different things, if I want to blend the two high-level concepts in the same code and to generate two different images, each of them will have less bandwidth to use. And so through this weight sharing constraint, it kind of naturally encourages them to generate the same stuff. And this is possible because we can use the same high-level code to describe the same the image of different modality from the same thing. Yeah, so this is the key idea. And for detail, please refer to the paper. And we found that it works quite well for human faces. So here you see what we're trying to do is we want to map a random number z into a pair of faces. One domain is defined by smiling faces, and the other domain is defined by neutral face. Okay, and it's not a conditional model. It's just a z to two faces, and we do the weight sharing, and at the end, through the GAN architecture, you will be able to generate a pair of corresponding faces, smiling, non-smiling. And when you move the z vector in the latent space, you can generate a transition from this person's face to another person's face. And although you are transition from one person to the other, the generated images are always in correspondence. The smiling face of the person, from A to B. And for this, it also works for ladies. Other example is again smiling, non-smiling, and moving along the z direction. Smiling, non-smiling, smiling, moving along the z direction. So here is about some gases and gases and without gases. Again, we can generate pair of corresponding images, even though we don't have any corresponding data in the training data set. And we change the z, we change the person, and always with gases and without gases. Sometimes it's strange that there's some attribute they change together. For example, you can see that the faces here seem to be is more pale compared to the bottom one. So some attribute they change together, which is quite interesting to observe. And also you can change the hair color. You input a random number z, and it will be mapped to two face images, one with blonde hair, the other without blonde hair. Again, changing the z, you have the change in correspondence. See another example. So this is all done in unconditional setting, from z to a pair of images. And we can also generate color and depth images. Again, we have a data set which only consists of color images of indocing, and another data set only have depth images of indocing, no correspondence. But through this GAN training, you can generate corresponding images. And you change the z vector, you get a different zone, and the depths and color are in correspondence. So this is another example. Because this is the unconditional setting from z, so the result is not so nice. But later on, we'll talk about what you can do in the conditional setting. So kind of quickly go over how to learn the joint distribution from marginal samples from marginal distribution using the GAN framework. So now we'll be talking about other type of distribution we would like to learn. Apparently, what we observe is time series. We always observe videos. We would like to be able to model videos using GAN. So last year, Karl von Zwick, they published the very first work on using GAN for video generation. And this is their model. So they start with a 100-dimensional noise vector. And their generator consists of two parts. The first part try to generate a 3D volume, a spatial temporal volume, which is supposed to represent the foreground, the motion of the main object in the foreground. And the bottom stream try to generate a background. So this model is for modeling video with static background and moving objects. So they have a background here. And now you can, at the same time, they also predict a mask. So for which pixel you're gonna take it from this spatial temporal volume, and for which pixel you're gonna take it from the background. So it's more like a foreground segmentation. So by combine these the output, and you have a video. Okay, this video is sent to a discriminator, spatial temporal discriminator, trying to differentiate is a real video or synthetic video. And through this training, you are able to synthesize video from random number. Okay, so in this formulation, each point in the latent space is a video clip. Okay, I just want to emphasize here. And they are mapped to a spatial temporal volume. So this is the result they get. It's kind of some reasonable stuff, but still, I think it's safe to say it's still far away from the real videos that we observe in real life. But it's a very important first step. It's possible to attend the GAN structure for render videos. So we start to look into the problem, and we start to think about what we can do to make it better. So this is a paper we recently published to archive. So basically, we try to model the latent space differently. So if you remember in the earlier work, they try to put each point in the latent space as a video clip. So here we try to consider a different formulation where we decompose the latent space into two parts. One is called content. It describes what kind of objects gonna be in this video clip. And the other, we call it motion space. But basically, each point is a pose configuration of the objects. And the change of the pose configuration, jumping from one point to the other, define a trajectory of motion. So we basically try to use this content and motion space as the noise to provide to the generator to generate the video clips. And what the benefits we can get from this formulation? One is that, okay, now you fix the content, but use different trajectory. You can synthesize the same person doing different expression. From, for one trajectory it can be fear, for another it can be disgust. And now also, if you fix the motion trajectory, but you have a different content, you can synthesize different people perform the same expression. So you get these additional benefits by performing this content and motion separation. So with this model, the latent code have two parts, GC content and GM motion. GC is fixed for short video clip because in a short video clip, we don't expect the content change too much. And for the motion, it's coming from, it's a trajectory. We use a recurrent neural network to generate a sequence of pose configuration, which is our motion trajectory. And we use this model to train again. This is our architecture. It looks complicated, but it's actually quite simple. The key thing here is we are not using video value generator. We are using image generator. At each time step, we have a latent code ZC, the content, and GN, the motion, concatenate, become a Z, puts into an image generator, you have a frame. And by keeping running the RN, you have different motion code. They are always concatenated with ZC, so you have then through GI, the image generator, we convert a sequence of images, a sequence of latent code to a sequence of images. Okay, so now we need a discriminator to see if we are doing a good job in the generation. And we do the following. Instead of using one discriminator, we use two. So we have two discriminators. One is called DI, which is an image discriminator. Basically, we randomly sample one frame from this sequence and try to measure this one looks like a real images. And we also want to measure this sequence is video, so we randomly sample T consecutive frame from this sequence and try to see if this is a real video. And through this simple architecture, we are able to do the motion and contents separation for video generation. So here, the learning problem for this architecture is simply an intention of the original GAN training objective. Here you have two. One is you have the two discriminator. One is a DI and DV, right? So you want to measure the random frame sample from true video clip should be considered as true, and random frame sample from this generated video clip should be considered as false. So this is the objective for DI. For DV, you want them to a random clip should be from true video clip should be considered true, and random clip from a fake one should be considered false. So you have this objective for training DV. And for GI and RM, where GI is our image generator and RM is the recurrent neural network, all you want to do is to measure the GI can convert a latent code to a good image, and the RM will give you some temporally meaningful sequence so that you can convert to a temporally coherent information, which is the video clip. Yeah. So this is a video showing the result. We can then generate, by using the same latent code, different motion code. We can generate the same person doing different expression. And by moving in the Z space, we can come out with a different person doing the same expression. And another thing about this architecture is that people spend a lot of effort in, from the first part of slides, people spend a lot of effort to come out with a better image generator. So it means that this architecture can immediately capitalize on the efforts in the image generation to improve video generation results. So this is a comparison. For VGAN, and we call this MOCO GANs, motion and content decomposed GANs. So, and the previous work from the MIT is called VGAN, the video GAN. Okay, so here is a table comparing these two architecture in the feature based on their features. So in the VGAN, the video generation is done by mapping a latent code to a video volume. It directly generates 3D volume. And in MOCO GAN, we generate frame one by one, sequentially. And the generator in VGAN is a motion dynamic video and a static background. And the MOCO GAN is image. And the VGAN has one discriminator, spatial temporal CNN. And MOCO GAN has two. One is the image discriminator, the other is the video discriminator. And in VGAN, it's always map an image to a fixed size, a latent code to a fixed size video clip. But for MOCO GAN, you can keep running the recurrent neural network, so you can generate dynamic variable length video clip. And in MOCO GAN, you can also achieve motion and content separation. And we do a user study on face generation and found that the MOCO GAN generates much better looking faces compared to video GAN. And I think partly because we are using video image generation model, which has better architecture, well understood performance. Okay, so this is the, okay, so it's about the joint image distribution and video distribution learning parts. So in the last part of the tutorial, we'll finally talk about computer vision applications. So before we start, I would like to say that since 2012, we have observed a paradigm shift in computer vision, right? In the past, I remember when I was a graduate student, we spent quite some time in understand how to design a feature for better discrimination task. And nowadays, we don't do that. We just design a network and train end-to-end and extract some nice deep feature, and we can do a very good classification task. So deep network kind of allow us to do this shift the focus from handcraft feature design to network designs. Kind of quite nice. We don't need to study something that's understood. With the generative adversarial network, we can help to solve another key problem in computer vision. So in computer visions, sometimes we are doing with something that's quite abstract. For example, it's quite difficult to define what is a host, right? In verbally, or you need a lot of words, or different, and there are many different ways to describe the same thing. But generative adversarial network provide you one key benefit. You don't need to do it anymore. You just need to collect a set of training images which describe the same stuff, a bunch of hosts image, and you will be able to generate a host. Given the training problem is solved, and also a bunch of airplane, it define image of airplane, it define the airplane. So this way, what it does is that in the past we do hand design feature, right? And we do hand design feature and the hand design objective function. So with deep network, we don't do hand design feature anymore. And with this generative adversarial network, we don't need to hand design our objective function. We don't need to specifically say we need this in our code function term. We just use data to define what we want to do. Okay. So there are many ways to use GANs, but I think the most general form is image-to-image translation. So the image-to-image translation defines a problem that you want to learn a module, an image generator, which map an image from one domain to another domain, a corresponding image in the other domain. So then we will use S1, S2 for two different domains, and one thing I want to highlight is correspondences can mean different things in different contexts. Okay, so this application, image-to-image translation, has a lot of applications in computer vision. One, for example, we have been working on low resolution to high resolution mapping. We have been working on deblurring, which is blurry image to sharp images. And we also do cross-domain from thermal to color. And we also do from synthetic to real. And low dynamic range to high dynamic range. Denoising, low energy to clean. And style transfer, image to painting. And day to night, weather change. So many computer vision problems can be approached from the image-to-image translation perspective. So this is a very general computer vision problem. So it has been studied many years, actually many decades. And along the year, different approaches has been exploited. Earlier day, we use a filtering-based approach, like a bilateral filtering. And we also do optimization. You can solve some formulated objective function and minimize that objective function. You can obtain, say, colorization. You can also do dictionary learning. And in the last few years, there was people try to actually train deep network to generate corresponding image with a corresponding data. You can directly do feed-forward approach. And now, I think recent work has shown that GAN-based approach is a quite promising direction to solve this image-to-image translation problem. Okay, so before we talk about that, let's just quickly review the GAN formulation. So you have a generator, converts, in the original GAN you have a generator, converts a random vector Z to an image. Discriminator differentiate one from the dataset, should be considered true, and the one from the generator should be considered false. Okay, and the training is done by alternating two steps. One, keep the discriminator fixed and update the generator, and the other, keep the generator fixed and update the discriminator. And the training GAN is minimizing Jason-Shannon divergence between the model distribution and the data distribution. So in computer vision, so this is unconditional model. We just start from random vector Z, you sample from your computer. But most kind of application papers are based on conditional GAN. So what it means is that we are not sample random number to generate image. We start with an image, low resolution image, and we generate to high resolution images, noisy to clean, daytime to nighttime. So we start with S1, which is an image from one domain. And we through this function F, we want to map this image to the other domain, so that the discriminator cannot differentiate real image from the second domain and the one coming from this F function. So this is the conditional GAN formulation, which turns out to be the most, I would say, most useful form for computer vision applications. So the formulation is quite straightforward. Instead of sample from a random number Z here, you sample from a true image, a data set. And then you have to map to the other domain. And then you want to make sure the discriminator cannot tell it is fake. And for the discriminator, you do the same thing. Just the image coming from the from the generator is a conditional model based on S1 and mapped to the other domain. And again, it's kind of minimizing the Jason-Shannon divergence between these two distributions, where is the data distribution in the second domain, and this is the model distribution for modeling the second domain, but you are using the image from the first domain as input. So conditional GAN alone is insufficient for image translation. What I mean is you generate some image, as long as it looks like a real image, it's fine. It doesn't need to relate to the input image in any way, right? So conditional image alone is insufficient for image translation. So you need an additional constraint to help you to map an image to a corresponding image in the other domain. And so by running conditional GAN alone, there's no guarantee that the image is translated to a corresponding image in a desired way. And so in order to add additional constraint to get what you desired, you need to do something. So in the supervised setting, where you have image come as a pair, you always have a daytime and a corresponding nighttime. Means, since it's much easier, like a low resolution to high resolution, you can artificially downsample an image and you can get a low resolution version. Okay, in the supervised setting, it's quite easy, and that's why it's first explored. In this CVPR, I think Twitter has an amazing paper on image super resolution. It's based on this idea. You have a supervised pair, and you have an image, low resolution image, and use a F function to map to high resolution image. To measure the generated image looks like the original one in high resolution, they try to measure the content between X and the input is the same. And the way they do it is to minimize the L2 loss and also the VG loss. Try to capture the content correspondent in more abstract fashion. So by minimizing these loss, you establish the correspondence. So that's a figure from their paper. So they show that if you apply bicubic interpolation, you get the blurry images. But if you directly train a deep network and in the discriminative fashion, you can learn to map a low resolution image to a high quality, high resolution images. But if you add a GAN nodes, you can generate even more realistic image, even though the PSNR value or SSIN value is lower than the one that's without GAN, but it's more appealing to human viewers. The reason is simple actually. We don't know how to describe high resolution images like verbally, but with showing the network a bunch of high resolution images, you don't need to do that. You just need the network to figure out how to do the differentiation. So we also have another amazing paper from Berkeley on the pixel to pixel. So it's the same idea, but more general. It's for many domains. The way they relate the two domains is to use supervised those pairs. What they do is the discriminator now take a pair of images as input. For those coming from the true distribution, it's just a pair of data from the training data sets. And for those from the synthesized distribution, you take a one from the input and this one as input, and the converted result you presented a pair. So through this adversarial training, at the end you will be able to differentiate a true pair of real images from a fake pair of real images, and this way you can learn the translation. And as we talked about earlier, these methods should be much more robust, but they require corresponding data or paired image, which can be difficult to collect in real applications. So then this kind of, okay, sorry, I should talk about this first. Again, my brain can be a little bit blurry, so if something is not clear, just let me know. So this is the result they show. So they show that they can convert semantic label to image. They can convert this another for facade, and from grayscale image to color images, or from satellite images to maps, winter daytime to nighttime, hand drawing to images. Quite amazing. And they don't need to use a lot of images. It's, for some examples. So as I said earlier, paired data can be difficult to collect, so it's motivate the research on unsupervised image-to-image translation. Okay, so in this setting, you have two data sets. Images from one domain, say daytime, and image from the second domain, nighttime. Okay, with no correspondence, we need additional constraints or assumptions for learning image-to-image translation. There's no free lunch, yeah. So, Apple's SYNGAN paper make an assumption like this. So, it's Apple SYNGAN paper is for kind of converting synthetic images from graphic engine to like a real image. So they want to make the annotation in synthetic image remain the same, so they can use that label for the translated image to inherit that label, and such that it can be used for training a classifier. So in order to measure there, what they can do is to measure that the input image and the translated images, they are similar. What do I mean here is they add additional cost here. So now, here is the GAN loss. I think you probably see at least 50 times during the presentation today. So you have X1, which is synthetic images, and use F to map to real-looking images. Not only that, you also want to measure this translated image and the original input image is similar in the L1 sense. So it kind of try to preserve the content. And through this, they show that they can convert synthetic image to real images while still preserve the gate location. So this is one way to do unsupervised image-to-image translation, but specialized for synthetic images. And this is probably one of the most exciting the papers in the last, since the beginning of this year, the cycle constraints for unsupervised image-to-image translation. So what this idea is about? Okay, so if we map one image, an input image, okay, from F12 to means map from the first domain to the second domain, and you again map this one. So this is a bit clutter here, but think about if you also when you do this mapping, you map an image from the first domain to the second domain, right? You also train a mapping image from the second domain to the first domain. So you can, through this path, you can convert an image from the first domain to the second domain and back to the first domain again through the F21. And what this cycle constraint hypothesizes is that through these applying these two F12, F21 in sequential order, it should be able to reconstruct the original input image. So this is a cycle constraint in this way. So they show that when you apply this one, and you also make sure that the intermediate output, say when you convert S1 to S2, this one has to look like a real image from the second domain. You actually translate this image from the first domain to the second domain. So this cycle constraint is discovered by a couple of different groups. They probably work on the same idea about the same time, independently. So we first seen the disco GAN paper from Korea and the cycle GAN paper from Berkeley. So it's based on the same idea. If you map an image to a corresponding image in the second domain, you should be able to map that image back to the first domain. So this is the idea. So the assumption here is this cycle consistency. Okay. So they show quite amazing results on painting to photo, and also zebra to horses, and the weather, different weather conditions. And I think I don't need to talk too much about cycle GAN because I think everybody know about it in Twitter. So, but there's a cycle constraints, one assumption people used to help solving this difficult unsupervised image-to-image translation problem. There are other ways. Another way people use is to share the latent space constraints. So like I said earlier in the GAN paper, we actually assume image of the same scene have the same high-level representation, and the use is to generate a joint distribution from samples from marginal distribution, right? So this is you can use this share the latent space constraint to achieve the unsupervised image-to-image translation. With GAN, what you can do is again just recap that we share the high-level weight. So it's effectively decompose the generator G1 for first domain to two parts, a low-level generator and high-level generator. Map Z to some representation and then map to an image in daytime, and map Z to some intermediate representation and map image to a daytime. And by doing this constraint, you can learn the joint distribution from samples from the marginal distributions. And once you have this joint distribution for an input image in the first domain, you can find a latent code Z such that you will be able to generate an image looks like this input image. And once you have this latent code Z, then you can apply to the second the generator from the second domain to generate a corresponding images. So this is another way you can do the unsupervised image-to-image translation. So, but for using this approach, you have to be able to solve this optimization problem, right? You have to find a Z which apply the first generator will give you an image looks like your target image, so that you can get the code applied to G2 to get a translated image. So this optimization has two drawbacks. One is it's slow, and the other you have to define the image similarity metric. If you use Euclidean, again, it can be blurry, so it's not so desirable. So this motivates us to do, okay, one more thing. This is unconditional model. It's based on Z. Okay, so this motivates us to do the conditional model. So you want to have a front end that can take an image as input and convert to the other domain. So what we do is, what we figure out is we can use architecture, we call it co-VAE GAN. So basically, this is the first domain. You add an encoder in front of the generator. And this encoder takes an image from the first domain as input. So you have encoder for the first domain, decoder, generator for the first domain, discriminator for the first domain, for data image. And similarly, you have an encoder for nighttime, generator for nighttime, and the discriminator for nighttime. Through this architecture, you can do image translation in this way. So you have, so for input image S1, you map to a latent code. And because you apply weight sharing here, you kind of map them to the shared latent space. Okay? And this shared latent space can go to G1 or G2. When it's go to G1, you basically do image reconstruction, right? Input image, and you want to make sure the output images, it's a VAE, so you basically reconstruct the input image. But for the cross domain, you basically want to generate a translated image. So here you can see that we have G1, E1, X1, which is the reconstructed image. We measure it's like a real image through this discriminator. But for this cross-domain pass, and input S1 from first domain, latent code, go to the generator in the second domain, you have G2, E1, S1, translated images. You want to make sure it's like a nighttime image. And you can apply the same thing for the bottom one. So this way, you can learn image translation unsupervisedly. Yes?
Those cross-paths
yes.
You're connecting, I'm assuming that they don't contain information about how dark the nighttime image you just included was?
Yeah.
It's just like that there was a chair and there was a patio.
That is true, yes.
Okay.
Yeah.
I was just wondering about that.
Okay. And to train this network, you basically add a VAE objective and a GAN objective. And I think you guys have seen a lot of equation today. So I will now explain this one. So it's basically VAE plus GAN. And let's talk about intuition, why this work. So in the to explain why it works, we can start with supervised setting. You know, if we have a depth image and a color image in correspondence, and you know, in supervised setting, we can actually try to enforce this E1 into map a pair of image to the same latent code in this latent space. And then we can use them to generate a pair of corresponding image. So this supervised setting. But in reality, in the unsupervised setting, we don't have this correspondence. So in this case, a depth image in map to a latent code, and you have G1 and G2. Even you use a discriminator, it will generate, say, through G1 you generate a depth image, reconstruct the depth images, and G2 you generate a color image. It's not necessarily, it does not necessarily correspond to, it's not necessarily a corresponding image of these depth images. It can be something arbitrary. As long as it looks like a real color image, it's fine. The discriminator only asks for, it has to be real looking images. Now, when we apply weight sharing, again, we limit the capacity. The G1 has limited freedom to generate a depth images. G2 has limited freedom to generate a color image. If they still generate two different images for the same latent code, the high-level feature vector have to encode the two different stuff. So, and each of them will not do a great job. But if they figure out they can generate a pair corresponding one, each of them can maximize the use of the capacity in the generator, and they will be generating a corresponding image. So in this case. And we can do the same thing for the second domain. and then you can learn how to translate image from one domain to the other. So this is just a benchmark that we have 6 networks here. If we remove some of them, what's it gonna be? So of course we present the best architecture. So all you need to know is when you use 6 networks, it's giving the best result. And this is some translation result we have. So we are quite interested in street scenes. So focus most of the results are in the street scenes. So here is the thermal IR images, and we were able to unsupervisedly translate to color images. And again, from color we can translate to thermal, and daytime to nighttime, and nighttime to daytime. This is all done without any correspondence. So you'll see that the result is not perfect. For example, for these images, I don't see the street light here, but it kind of generates 2 light bubbles. But it looks like a real color images. So it means the GAN trying to make it real. Okay, what I should say is that the capacity constraints help generate corresponding one, but it does not guarantee you will have a corresponding one. It also depends on many other factors. Okay. So this is another result for the sunny day to raining day, and the raining day to sunny day. Below is we kind of use synthetic data to show that we can make a foggy image looks like sunny, and yes. Yes, I think it's possible. So if you have any supervised pair, you can do semi-supervised image translation. And also one thing interesting is cycle constraint is one assumption. Shear latent space constraint is another assumption. They are compatible. You can, I think you can jointly use them for image translation. And there are other ways you can use. So we thought about many different approaches to improve the result. Just haven't had time to do one by one. So. But I think it's possible. I think the key thing is you need to use the right assumptions. Yeah. So, and way more assumptions. Yeah. To regularize the translation. Yeah. Oh, I don't know why I show it twice. But okay. So this is a sincere data set. Kind of give confidence if you have enough data, it gonna work. And with less noise, in the synthetic data. So I think with more effort, probably will work for real setting. So I'm very happy thank this Ian Goodfellow. So he kindly provided his image for me to try out the translation task. I think I missed one slide before. Yeah, okay. So here are the slides. I think you can apply, you can define domain by attribute and do the attribute-based phase translation. It's different to what Julie showed earlier. What Julie showed earlier is the conditional model, condition on attribute, and you can generate different images. So in this model, you use the first domain is all like a image without blonde hair. The second domain is all image with blonde hair. Then you can learn a translation from black hair to brown hair. And with another setting, you have an image with no eyeglasses and image with eyeglasses. And you can do the translation from no glasses to eyeglasses. And you can add a goatee. So I think Julie said that there's no ladies with goatee. So it's difficult to achieve it with conditional GAN. But for this unsupervised setting, when you train separate two generators. It's actually can put some goatee to ladies. I really feel sorry for the celebrity that I use for these experiments. I hope they don't mind, but it's kind of really give some convincing goatee to these ladies. And yeah, also there are other attributes and also work for men. Since we published the paper, it's a couple of different group. We didn't release the code, so there's a couple group implement independently. Some of them try to do the male to female conversion, and it seems like it doesn't work quite well for male to female. So I think there's still a limit how much this model can achieve. So here is an example try to apply to Ian Goodfellow's face. So again, to this, so I am a researcher. I try to provide the most general setting, and but if you want to apply to products, there are many things you can do. For example, I use non-frontal face and frontal face for training. You probably just need a frontal face, and I don't do any face alignment. I just simply covalent. If you do face alignment, it can be better. But just show that it can generalize to face image that wasn't in the data set, not in the data set. So you can give him Ian blonde hair, put eyeglasses, and make it that's neutral, and can try to reduce the goatee. And actually, you can apply the model and again, and with reduce more goatee, you can apply sequentially. So I try not to do that, but there are many things you can do to make the result better. And this is our CEO, Jensen. She also allow me to use his images for illustration. So can add blonde hair, eyeglasses, and make him smile or add some goatees. So finally, conclusion. So we're gonna conclude the entire tutorial. Okay, so we start with talk about the family of generative models from VAE, autoregressive models, pixel CNN to GANs. We kind of put them in a tree, kind of tell you what the difference. And we talk about theory of GANs. The key thing is the discriminator try to approximate the optimal base decision rule. And but we don't directly control the density. So what we do is approximation. And the capacity of discriminator determine the kind of has effect on the mode classifying problem. When the discriminator has low capacity, it doesn't need to remember, generator doesn't need to remember, doesn't need to learn, capture all the modes, but it will still be able to optimize the objective function. So these two things are tight. And we talk about various training techniques, right? Like a tricks-based, objective function, distance-based, and other auxiliary objective function, and the change in network architecture. There are many tricks. But the key problem actually in this field is we don't have a good evaluation metrics. So it's really difficult to compare one paper to the other. And some people say that if you combine two different work together, it doesn't work sometimes. And then we move to the switch gear to the joint image distribution learning. We talk about the co-GAN, and the video distribution. We talk about the video GAN and local GAN. And the last part is image translation, supervised setting and unsupervised setting. And thank you for all of your times. And I said the tutorial is already online, and feel free to drop me emails for further discussion. And now, is any questions? Thank you. So, yes.
I have a couple of questions. What is the criteria to stop the training? Where do you say now training is done?
So for different methods, they have different criteria. So far, the best one work for me is to use my eyes to check which one. Yeah. So, yeah, that's the problem. It's randomly initialized for the works I talk about today, but I know there are works using a pre-trained network. Those discriminator is pre-trained. So it's possible, but we didn't cover these works in the tutorial. So no, to your answer your question. Yeah. Yes.
Roughly for all these different techniques you've gone over, how long does it take to generate an image and to train on, say, a Titan X? Is there like a big variety?
For faces, it's very fast. You probably maybe few hours you can see very good results. It depends on image resolution and depends on the data distribution. It depends on many things. So yeah, for faces, it's very fast.
So what I showed as a demo was running live. There was a little bit of lag PC because it was running on Santa Clara. It was running on my workstation on an M6000, which is the workstation version of the Titan. So that's the order of
Yes.
Just going back to stopping training criteria.
Yeah.
My understanding was it's basically that the discriminator can't tell the difference.
Yeah.
So presumably there's some kind of threshold that the number of examples that can or can't tell the difference.
Yeah. Yeah. So in WGAN paper, they train the discriminator fairly well. So they kind of use it to determine, to measure the progress. But for other works, they do one update to the discriminator.
Sorry?
Huh? Oh, in the WGAN paper, Wasserstein GAN paper, they train the discriminator for a couple of iterations before updating the generator. They claim that this discriminator is closer to the optimal one, and they use it as criteria to update to determine when to stop or to measure the progress. But for many other works, they only update the discriminator once, and hence it's not a good metric. And also the discriminator may not be well trained, so it may not be a good metric. Yeah.
But the discriminator goes through many iterations.
Yeah. Yeah. Yes. Uh-huh. Sorry, can you say again? Oh, alignment of data. I would say, actually, I don't know. I mean, if I'm working on applications, I will make sure it's aligned to the, try my best to align them. So, yeah, I don't know what is the good.
The easy answer, it depends on data.
Yeah.
It's actually a very, very difficult question. It's very dependent on the data set you're training on.
Yeah, that's why I talk about training, spend a lot of time in training. I think the solution is to find out a very good training approach. Then it works for any data, any architecture. Then we kind of make, if this happens, then we make a big step towards solving many vision problems. Yes? So I think the problem is still on the manifold. So I think if you remember in the one of the slide, I showed that the mode recovery rate actually correlates with the manifold dimension instead of data dimension. So you can map, so for example, you have the celebrity faces. You can say do some bilinear upsampling. You can map to high dimensional space. You will be still able to learn faces, but you can learn it because the manifold is in low dimensional space. It's easier to capture. So for example, if you want to model dogs, I think the manifold is more complicated, more high dimensional. So in that case, if your data dimension is quite, it doesn't matter with the data dimension. It's because the manifold dimension is high, it's more difficult to learn. Yeah, that's my answer. Yeah. So the resolution thing, it should work for faces, but for other, we haven't seen successful results. Yeah. Yes. Sure. Oh yeah, I think what I feel safe to say is that if your output, your something you want to generate is closer to images than label, GAN will be more helpful. So if you want to do super resolution, it will be more helpful. But if you want to do other, for example, you want to use discriminative to extract attribute or those like a low dimensional output, I think I would still prefer using supervised training instead of GAN training. I hope it answers your question. Yeah.
You also mentioned that GAN can replace objective function that we don't have the kind of design.
Yeah.
But in your slides, you have shown several objective functions that people have proposed
Yeah.
for training GAN.
Yeah.
So can you elaborate what you mean by that?
So what I shown, I think you talk about here. So we see many objective function, but even though they are using different objective function, they're based on the same concept. They are using data to define their objective. The different objective function is just different way to measure the distance between distribution. Like just even before GAN, we have chi-square, we have K-O divergent, we have Jensen. We have many different way of measure distributions. So yeah, and my gut feeling tell me that I feel like what's more important seems to be the auxiliary objective function. That's just my guess. If you ask me to guess which one will win eventually, I'll prefer this auxiliary one. Yeah, this is just my personal opinion. I might be wrong. I might be terribly wrong. But just tell you, if you ask me to guess, I will guess this part. This one. The auxiliary objective. I may be wrong, so it doesn't work. Huh?
I think you're referring to something similar to, like, for example, star transfer, right? There are like multiple different choices there, and then about the grand star transfer was the best approach to solving this problem. But like in this case, like in terms of the star transfer with like generative adversarial networks, you don't need to pick a specific objective function. Instead, you need to just pick like, is it something that Picasso did?
Yeah, so that's the idea, right? So in the style transfer from Getty's work, you need to have an image as a guidance, tell you how to transfer the style. So here, you learn a mapping function, and the mapping is defined by the data. So you use a lot of, say, Picasso's picture paintings to define your goal. Yes. All right. Thank you all. And slides is online. Thank you.